Hello students, welcome back to my class. Last time we have discussed about vapor refrigeration cycle and the pH diagram of vapor compression cycle, and also the temperature entropy diagram of vapor compression cycle. So, let's revise topic what we have done so far. So, last time we discussed about this, that uh, uh, what is pressure enthalpy diagram and how the vapor compression diagram is drawn in pressure enthalpy pressure enthalpy chart, as you can see uh, in this diagram. We will revise it what we have done. Mm, so this is from 2 to 3 the processes compression, and 3 to 4 the processes condensation, and 4 to 1 is expansion, and 1 to 2 is uh, evaporation. In the process 1 to 2, the evaporator is absorbing heat from the space which is to be cooled, and from 3 to 2 of 3 to 4, the condenser is also a kind of heat exchanger which uh, rejects the heat to the surrounding. So these are the main components. In a general manner, you can say that the evaporator extracts heat, and the condenser supplies the heat to the surrounding. And now you can see from 2 to 3, there is a compression which increases the pressure of the refrigerant and causes it to flow throughout the system. And from 4 to 1, there is expansion device which uh, reduces the pressure and simultaneously reduces the temperature also, and turn the high pressure, high pressure liquid into low pressure, low temperature liquid, which causes cooling. So today, this is your pressure enthalpy diagram, and this one is your temperature entropy diagram for vapor compression cycle. Let's revise it again. The temperature entropy diagram. In this diagram, you can see that from 1 to 2, this is compression. And it is isentropic compression. That's why the entropy is constant from 1 to 2. As you can see in this case, the entropy at point 1, the value of entropy at point 1 and the value of entropy at point 2 is not changing in the process of compression. That is why it is adiabatic compression. After that, 2 to 3 is condensation. In this, the temperature decreases due to a rejection of heat to the surrounding by the heat exchanger. So in this case, the temperature of the refrigerant is also decreasing, and from the superheated vapors, the refrigerant is turning into liquid. after that, this high temperature refrigerant is passing through expansion wall, due to which there is a increase in entropy from 3 to 4. The process is expansion process, and you can see the value of entropy is increasing due to expansion, and temperature also decreases simultaneously. And due to expansion, the pressure is also decreasing. And after 4 to 1, the process is this is evaporation. In this, the heat is absorbed from the space which is to be cooled. Actually, 4 to 1 is representing that this is the refrigerating effect, that how much heat it is extracting. In enthalpy diagram, we can see that 4 to 1 is refrigerating effect, where it is producing refrigeration due to extraction or absorption of heat from the space which is to be cooled. So uh, mathematically, we can write it like this, that H1 enthalpy at point 1 minus enthalpy at point 4 is the amount of refrigerating effect produced by any refrigerator or vapor compression cycle. So this is refrigerating effect, the amount, and you can see that what is COP. We have already discussed about it. So we know that COP is refrigerating effect upon work done. So this is the refrigerating effect, that is H1 minus H4, and the work done is work done by the compressor, which is from H2 minus H1, as you can see. The next topic is in this topic we are changing some conditions uh, of the vapor compression cycle, and we want to know that what effect we will get out of it. So to understand it better, we studied about the pH diagram. Now you can see, now they are telling that when the vapor is dry and saturated at the end of compression. So uh, as you can see, this is the compression process from 1 to 4. We know that this is your liquid saturated line. Sorry, this is your saturated vapor line, and this is your liquid saturated line. So at the they are saying that at the end of the compression, we are getting saturated vapors. So this is the point 2 is the end of the compression process. So it means uh, this point 2 is coming over the saturated vapor line. So in this case, the diagram will look like this, and in temperature entropy diagram, you can see the from 1 to 2, the process is compression process. So at the end of compression, the point 2 is coming over the saturated liquid line, as you can see. So what are the effect of it? Obviously, uh, this is COP, coefficient of performance, that is refrigerating effect upon work done. So it's this is your refrigerating effect, H1 minus H4, and this is your work done, that is H1 minus H2 minus H1. The next is when the vapor is wet at the end of the compression. So they're saying vapor is wet. So mm, these are your dry vapors. Saturated vapors are also called dry vapors, but below this line, the vapors are wet. So that's why uh, the point which depicts the end of the compression, that is 2, that is coming behind this saturated vapor line or dry vapor line. the point has little bit drifted towards the left. Mm. So what are the effects of it? Obviously, uh, as you can see, the refrigerating effect is also decreasing the COP, the compression, the the work done by the compressor has decreased, but ultimately uh, you will not get cooling effect due to wet vapors. Uh, when the vapor is superheated at the end of the compression, so in this case, you can see, we will see the pressure enthalpy diagram at the end of the compression. uh, the vapors are coming into superheated vapor space, or region, and we are getting superheated vapors at the end of the compression. So what is the effect of that? As you can see, uh, the the refrigerating effect has increased in simultaneously to compress the vapors up to superheated vapors. The work done has also increased. Next is when the vapor is superheated before compression. So as you can see in this case, they are telling that when the vapor is superheated before compression. So in this case, they are telling that this point one, this is the process in general case, in general vapor compression refrigeration system. The pH diagram is 1, 2, 3, and 4. So this is the pH diagram of vapor compression. But if the vapors are superheated before the compression, so point 1 will drift toward the right and will start from here. So due to this, obviously the refrigerating effect have increased, and in TS diagram you can see from photo 1 the refrigerating effect have increased, and the work done by the compressor has decreased. But or you can by that the COP can increase. Um, but the thing is, to uh, to bring dry vapors up to superheated vapors, it requires high amount of work done. That's why the COP is in that case not increasing. When the refrigerant is subcooled before throttling. So in that case, we are doing subcooling of the um, refrigerant before throttling. So you can see that the process 3 to 4 is throttling process, and in this case we are providing super cooled liquid through uh, expansion valve or throttling device. So if we are providing subcooled refrigerant to the expansion valve, uh, then this point 3 will drift towards left of this diagram, because in that case this is the saturated liquid line, and before the saturated liquid line, the space there is a space which is called uh, subcooled region. So that's why this point is drifting towards 3 dash, towards left, or 3 dash in the region where the refrigerant is subcooled. And after that we are providing it, what is the effect we are getting out of it. As we can see, this is the refrigerating effect. Obviously, when we were not providing subcooled refrigerant to evaporator, uh, the refrigerating effect was less. But after providing subcooled refrigerant to the evaporator, the refrigerating effect has increased, as you can see. Uh, so there is a huge increase in refrigerating effect. If refrigerating effect is increasing, obviously COP will increase, because COP is directly proportional to refrigerating effect. It has direct relation with refrigerating effect. If refrigerating effect will increase, COP will obviously increase. And you can see the work done is almost the same in both of the cases. That's why it remains constant, due to which COP will increase. And the top of that, we have no need to do extra work to bring the refrigerant into super region. Mm. This is your effect, effect of subcooled refrigeration, which we have discussed previously. In that case, the refrigerating effect is increasing, and due to which COP is increasing. So generally, to bring this refrigerant in or to turn this refrigerant, liquid refrigerant, into subcooled refrigerant, and the refrigerant which is coming out from the evaporator, we are, with the help of this refrigerant coming out from the evaporator, we are cooling this refrigerant which is getting out of the condenser. We are we are reducing the temperature of the refrigerant which is coming through the condenser, with the help of refrigerant which is coming from the evaporator, because the uh, refrigerant which is coming out of the refrigerator, its temperature is quite low, and with the help of this we are cooling the refrigerant which is coming out of the condenser up to a little bit low temperature. uh, so in this case you can see that we are not doing extra work to cool it down up to the cool subcool region. So that's why the COP of this is quite high. Next is effect of superheating of vapors. So I think that's enough for today, and we will study about it in the